very much for joining us tonight at the virtual meeting of the Warren Astronomical Society. This, of course, would normally be our third Thursday Macomb meeting, and it is the week in which the Cranbrook and Macomb meetings happen 3 days apart, at which point I'm a bit glad that we're doing virtual meetings because that was always a pretty punishing week. So we've got the full slate of Macomb-type activities tonight, one speaker, and as we've been doing lately for the virtual meetings, we've been reverting back to the old tradition of having the officers give their reports in person, since we're all here. But first, we've got In the News and the Sky, and we've got our past president, Jeff McLeod, on deck to present to us tonight. You ready to go, Jeff? You're muted.
I said, yeah, we can start right now.
All right, let's take it away with Jeff McLeod.
Okay, here. Come along now. All right, are you seeing the In the News title slide?
Yes, we are.
Okay.
Yes.
So since we only had 3 days, I figured I'd do something a little bit different for In the News in the Sky, because I didn't think I would need that much time. And the slides are not advancing. There we go. All right, so what I'm going to do is cover some things that happened in the last 3 days. So in the observable universe, on average, 16 million supernovas have gone off. But we're not losing stars because 12 billion stars have been born in that same time. So we are still gaining stars in the universe, which is nice. Here at home, 51 meteorites large enough to actually reach the ground have hit in the last 3 days, 300 tons of dust. Here in Michigan, we've gone about 55,000 miles rotating around the Earth. We've gone about 4.8 million miles around the sun. The sun itself has gone about 37 million miles around the galaxy. And in those 3 days, the sun has converted 1 million tons into pure energy that we see as light. And some other random facts over the last 3 days, the Andromeda Galaxy is 17.5 million miles closer to us. The Voyager 1 spacecraft is about 3 million miles farther away. If you were a light beam, you would travel about 519 astronomical units, pretty darn far. And maybe the most impressive of all, particles at the LHC have gone around that track 2.9 trillion times since our last meeting. So someone's counting off quite a lot of revolutions there. This day in astronomical history, the 17th, in 1789, William Herschel discovered Minos around Saturn, sometimes called the Death Star moon. That's no small moon. In 1962, the second set of astronauts, the New 9 or Nifty 9, were selected. And some pretty famous dudes in that group: Neil Armstrong, Frank Borman, Pete Conrad, Jim Lovell, Jim McDivitt, Elliot C., Tom Stafford, Ed White, and John Young. I think everyone has a favorite astronaut in that 9. And then in 1976, NASA unveiled the Space Shuttle Enterprise. We have the crew of the Starship Enterprise viewing it with them. Diane gave a talk on this shuttle a few years back. This is the glider one, never actually flew in space, but is technically the first shuttle. So I just wanted to talk about Venus because this is really the big story, probably maybe even for the year, depending on what happens in the next couple of months. But let me move this so you can actually see the punchline of this meme. So big difference between finding phosphine on Venus and finding life. So that's the little joke there. I actually found a couple of the papers that have been published in the last couple of days. So what they think is going on here is that there may be a temperate zone in the clouds where microbial life can exist. If it falls too low, it dies. If it gets lofted up too high, it dies, but it can just kind of circulate in that middle zone, and you could have some sort of bacterial ecosystem there. However, if you look down to the bottom left here, the progenitors of phosphine, it's not necessarily a simple, you'd probably have to have a degree in chemical engineering to really make any kind of declarative statements about this plot here, but I'll just say that it's more complicated than my pay grade. So we're going to have to wait some time, and they're going to have to do some more investigating before we really know what's going on with this phosphine. Interestingly enough, reading the paper, they started looking at Venus to kind of have a benchmark of what they could do when looking at other exoplanets, and they weren't expecting to find phosphine, and then they found way more than expected. So the first paper was just, hey, we found phosphine in Venus, and then the second paper was, here's all the ways that it can't be made, and why we can't explain how it could be made on Venus. So that's where all the real excitement came in. And now my neighbor is starting up his mini bike. He'll be gone in just a moment. He seems to take a mini bike to work. All right, so yesterday the big news was Mount Wilson Observatory. From the reports I heard, they had fire about 500 feet away at certain points during the evening. But I believe the telescope has been saved, and there isn't too much damage to the observatories out there. For those of you that don't know, the Mount Wilson Observatory is where Hubble made his kind of famous discovery of, Andromeda Galaxy being a full galaxy and not just a nebula in the Milky Way. So a pretty historical site that they're trying to save, and hopefully that remains to be true. And then, so in the sky, nothing too crazy coming up. I just wanted to break down a couple of things that I found playing around with Stellarium. So on 9/18, we have the Moon and Mercury. Pretty hard to see even in Stellarium, so good luck to you. You're going to have to go out right after sunset, get pretty good western horizons. But if anyone is up for the challenge, that's a pretty good one. This is the time to do it. The 22nd at 11 p.m., we have an Io transit with the shadow. And this is a pretty good time, not too late. And you also have the red spot there. So if you've not done a Jupiter shadow transit, maybe check this one out. There's some other ones coming up, but I think this is probably the best one in the next couple of weeks. On the 22nd, we have the fall equinox. Nothing really spectacular to go out and observe. It just kind of looks like the sun. But this is when the sun's point on the ecliptic actually crosses the equator. And so if you actually plot these lines out, this is when everything intersects. So the days are even, and they're only going to get shorter after the 22nd there. And then we've been having some nice conjunctions of the moon. So on the 24th, the moon will be near Jupiter. Nowhere near as close as the moon and Mars was a few weeks ago, but still pretty good. And then on the 25th, near Saturn, we kind of miss the closest approach. It kind of happens when it's under the horizon for us, so that was kind of unfortunate. And then on the 26th, right after sunset, we have a Ganymede transit. Not the easiest thing to observe, but maybe worth the effort. And then on October 1st, we have another Io transit with the shadow. That one also maybe a little too early during the day. The sun hasn't quite gone down, so that one might also be kind of tricky. But I just thought I'd give you the times and dates, because if it's clear, go out and try. And then on the 2nd, we have the moon near Mars. Again, not quite as close as it was last month, but it'll still probably be pretty nice to look at. So that is, in the news, in the sky, this day in history, whatever you want to call it, for I'm still calling this a Macomb meeting.
Excellent, Jeff. That was a very stylish way to deal with that brief news cycle. For those of you, I was afraid, frankly, seeing the news this morning that Mount Wilson being destroyed was going to be the top story of Jeff's news presentation. For those of you who want to keep tabs on this, one of the greatest historical observatories in America. I'm a member of the Friends of Historical Observatories on Facebook, and they've been doing periodic updates from the scene. So right now, or rather, as of this morning, the Bobcat fire was menacing what's called the monastery there, the DC power to the domes, and some of the outbuildings, but not the domes themselves. So right now, it seems everything is still standing. The library was at risk. Some of the dwellings there are at risk. This is definitely scarier than the fire back in, I think it was 2009, the station fire. So just stay tuned.
Yeah, apparently they also had a pretty bad one back in '94. When I was trying to find images, I found a pretty gnarly burned dome from the '90s.
Yeah, Jonathan and I went up there a couple of years after the station fire, and the buildings were fine, and it was that lovely period after wildfire where everything is wildflowers. So that was life endures, but hopefully so will the domes and the Hooker telescope. All right, fabulous. Thank you, Jeff. We've got Adrian Bradley on deck next month to do the news in the sky for the virtual Cranbrook meeting. If you are interested in putting your own flair on In the News in the Sky, contact me or Dr. Dale Parton. And with that, we will take things away with the officer reports. So, as your president, we're still here, which is great. We've got an update from Dr. Dale Parton earlier this day that indicated that Macomb will not be letting us back for quite some time. So at least expect virtual Macomb meetings to be a thing into early 2021, which gives us some flexibility, even if we start resuming things at Cranbrook before then, because there's a lot of you who could meet us here on the internet that could not attend an ordinary Macomb meeting. So we've got our biggest thing on the calendar is, of course, astronomy at the beach. Bob is going to talk about that as part of his report, but I just wanted, as president, to remind y'all, astronomy at the beach is incredibly special. I was on the planning committee for almost a decade, having 7 or 8 clubs come together every year to put on something for the good of the Michigan public is amazing. We are used to astronomers doing fabulous star parties for ourselves, bringing in speakers for us, setting up telescope fields for us. But astronomy at the beach is for the public. And even though this time there is no beach and everything is remote, Bob and Adrian and the planning committee have put together an amazing slate of speakers, such as we could never have all in one place at one time in a physical astronomy at the beach. It's like a full-scale convention with multiple speaking slots and different activities to join. And they've really put work into making this a world-class virtual event. So I know I took off both days off work just so I could get in the right headspace and enjoy it. So I'm strongly encouraging you. Yes, you've been doing a million different Zoom events, WebEx events, virtual events this year. You may have seen some of these speakers before, but this is a really special event, and we strongly encourage you to drop in and enjoy what the committee has managed to stage in a crisis. They have done an incredible job. Beyond that, we've got banquet coming up. It's going to be a virtual banquet, so we've got really cool speaker lined up for that also. And we're working with the assumption that things are going to be for 2021, kind of like they are right now. So we're in a holding pattern with our open houses. We're in a holding pattern with any of our outreach events. But this has been, we've made the best of it, and it's been great to see you all every couple of weeks, or in this case, every couple of days. And if you are interested in joining the board, we do have some term limit type vacancies coming up. And so if you are interested in becoming a board member, the elections are in November. If you are interested in helping the board with the process of reconstituting, the nomination committee is due in October 1st. So we have a couple of weeks. If this is something you'd like to do, reach out to the board, let us know. We need 1 to 3 people for the nominating committee. And of course, we take up to 7 officers at a time. So if you have a dream of being on the board or a dream of helping select the board through the nomination process, let us know. And with that, I'd like to pass things to our program chair, Dr. Dale Parton.
Okay, thank you, Diane. One of the good things about having to have these virtual meetings is not only can some of our members participate who might not otherwise be able to, but we can bring in speakers from far off places to do presentations for us. At our next meeting on Monday, October the 5th, our short presentation will be given by Anne Blackwell, who is a graduate student studying astronomy at the University of Michigan. The title of her presentation is The Little Big Bangs. The full-length presentation on October the 5th will be given by Dr. David Levy with the intriguing topic, A Lyrid Meteor Shower, Getting Thrown Out of Dad's Will, and a Journey Through the Night Sky. Who but an English major could come up with such a title? So that's what's coming up. And as we will soon see, we have another speaker from way out of town tonight. Thank you, Diane.
Thank you, Dale. And now
I missed something.
Yes.
Sorry.
No problem.
That's for our next meeting on October the 5th. On October the 17th, Thursday, our quote-unquote next Macomb meeting, we will have Dr. Patricia Ann Stratt speaking on the topic, Is There Life on Mars? She has some history on this topic. She was one of the co-experimenters of an instrument on board a Viking spacecraft that landed on Mars back in 1976, and which appeared to detect life. So it'd be interesting to get her perspective on, is there life on Mars? Thank you.
Fabulous. All right. And now I'll pass it to Observatory Chair Riyadh.
Hi, Dan. Can you hear me? Okay, thank you. Yeah, I've had some audio difficulties today. So yeah, I went and visited the observatory on the 12th. Everything is fine. Both buildings are in good shape. The equipment is in good shape. Of course, the observatory remains closed at this time because of the virus until further notice. I guess now that it's starting to get a little bit darker earlier, if somebody wants to go out there, please make sure you observe the rules of the park, and if there are any state rules about social distancing and so on. And I think the park may be open till 8 o'clock at night. If the park officer asks you to leave, please leave. But otherwise, you may be able to start using at least the site, not the building itself, not inside the observatory, but you may be able to go out there and do some observing when it gets dark early enough throughout the upcoming winter. Other than that, nothing else is new. Thank you, Diane.
Thank you, Riyadh. And now, have we got Oh yes, we definitely have Glenn. There you are, Glenn. Glenn with the secretary's report.
Yes, Diane, the minutes for the Cranbrook meeting are out for board review. And the beg letters will start going out on 9/21 for the donations, that is. That's pretty much all I have to report this time.
Thank you, Glenn. The banquet may be virtual, but we hope that the prizes are real. And Glenn is in the process of getting them. Very good. I do not see Mark, our treasurer, on the line tonight, but the treasury report is in the WASP, and things are not remarkably changed from the Cranbrook meeting. So do check out the WASP if you have any questions about where we're at with the Treasury Department. And now we've got Bob Tremblay at Outreach with his biggest report of the year.
Am I there yet? Hi there. Can you hear me? Testing, testing.
We hear you.
Okay, good. Well, I just posted the Astronomy at the Beach link. We have an absolutely fantastic lineup of speakers for the event. If everybody would share that with absolutely everybody you know, especially teachers, that would be awesome. We are doing it online, obviously, and I am still putting stuff together for some of the events online. I need to get with you, Diane. I've got a good list of things for the on-demand. I would like a couple more, especially I'm putting together a resource page, which I hope to have done by the event. When I'd like to have some like mobile apps and websites that all of you guys send people to frequently. But anyway, so Astronomy at the Beach, the 25th and 26th. We are going from 3 o'clock until midnight. 3 o'clock is going to be 3 to like 6 or 7. We're doing solar, and we have a bunch of people broadcasting solar from observatories and driveways. And after that, we have lectures galore, and we have a kids track, which is pretty cool. One of the things that I'm really happy to see is we've got a teacher panel, which has my wife and Paulette Epstein on it, and I'm looking to get a couple more people for that yet. Other than that, been real busy working on that website. Kind of a shame it's only going to be a 2-day event. One of the things I have on the website that we've actually gotten one bite for so far is many of our presenters are solar system ambassadors, and many have said that they'd be willing to do presentations about astronomy and space science for in classroom and at home remote sessions. So we've already got one bite. Ken Burton has said he'd do that, so I got to follow up with him to see what they're doing. If we get inundated with requests on this, we're going to have to come up with something. But hopefully we'll get inundated with requests. I'm really looking forward to this event. I hope everybody else is too, because I'm gonna be really busy at it anyway. Did I leave anything out?
I hope not.
I can go yammering on about it forever.
Yeah, no, but it's again, I can't say how proud I am of you and Adrian and the gang for doing this on the fly. Just incredible.
Well, one of the things that I've commented on several times, this was started months ago when we're starting to get people ideas and come up with events, and I suggested doing panels. And I'm using a lot of my experience helping with science fiction conventions, and I'm actually modeling some of the things after that. And when we do the tear down and talk about what went right, what went wrong afterwards, I'm going to have some suggestions about assigning certain people for certain things, and et cetera, et cetera. So.
Oh yeah, the Astronomy at the Beach postmortem is always fun too. Anyway, fabulous. So yeah, next weekend, Friday, Saturday, be there or just be there. We're not doing an open house, a regular open house on the 26th, because what better open house could we all have than night 2 of astronomy at the beach? So, yeah. Thank you.
Diane, can I ask a question? To what extent has the general public been aware of this and able to participate?
We are publicizing the heck out of it. We've got a Facebook event people are sharing. Brian Odom was actually interviewed on, oh God, did he say? I can't remember. I think it was WDET, but he's been on the radio waves. I've been posting things, but that's why I'm saying, there's the link. Send it to people. Send it to everybody you know. We've got to ask the membership to, send it out. I would especially like to see a lot of teachers and students show up for it.
Thanks, Bob.
Yeah, no,
Oh,
good question, Glenn. But since GLAC has its own communications director as an official position, like that's all technically GLAC duties. And we as, we've always been more traditionally responsible for supplying the astronomers rather than supplying the general public. But they have a whole network of publicity things that Brian's been developing in his tenure as communications director over the past few years. So
one fantastic resource we have right now, a guy by the name of Mark Musen. He used to work with Starbase. He came and talked with us about a year and a half ago about Starbase. He now works at the Macomb Intermediate School District, which is my wife's school district. I sent him the Astronomy at the Beach blurb. He sent it out to every teacher in Macomb County and several different STEM organizations. So got the word out pretty good that way.
all right, fabulous. And since we could talk
just,
about yes, Jonathan.
I did. We haven't sent out any kind of email to our membership yet, and we do have 500 people on the membership email list. Is that something that we can do in the next week or so?
That is something I can do probably before the end of the evening.
Awesome.
That would be cool.
Okay. And that makes a nice transition to our final officer report. Jonathan at Publications.
Well, the WASP, as they say, is up. Dale
Yeah,
Teamy, our redoubtable newsletter editor, so far has not been blown away by Hurricane Sally, which took out a mile of the 3-mile bridge there in Pensacola. But he is without power or internet, so that's why he's not with us tonight.
Yeah.
But so far as I know, nothing got blown away except for his connections. So.
All right, and Jonathan is doing a Mars-themed, or rather, Jonathan and Dale are doing a Mars-themed WASP next month because it is the Mars opposition. So if you have any Mars-themed articles or other content, artwork, doodles, I'm looking at you, Jeff, to send into the WASP, Jonathan and Dale will be very happy to publish those. Okay. So that's the officer reports. I believe most of the subgroup chairmen are not here tonight. Solar Marty is not in, but we talked last night. And believe it or not, NASA and the NOAA have declared Solar System 25 is on. They actually had a teleconference on Tuesday. So we have begun the new solar cycle, but the sun right now is dead boring. Astrophotography, I believe Bill, along with a lot of our astrophotographers, are up enjoying the Great Lakes Stargaze, which went on. They're up there doing their thing, engaging in physical distance observing, and slightly inconvenienced by the wildfire smoke-tinted skies. So I'm sure they will be coming back down with a batch of good astrophotographs. I've already seen a couple of preliminary images from the gang. Then we've got history subgroup. Dale Teamy, as Jonathan said, is currently without power or internet. And Jonathan, I think you're the last subgroup captain standing.
We're gonna try to get everybody's Astronomical League stuff in order. So keep keep your eye out for that.
And Jeff is our discussion
And
group
if you wanted
captain.
merchandise, he would have let me know about it by now.
And Jeff is our discussion group captain, but those are not being held in person for the time being. So yes, our subgroups are in a bit of a state tonight. Anyhow, that gives us some time for observing reports. There weren't that many at Cranbrook, but I know somebody somewhere has gotten out a telescope and had a look at something cool in the last 3 days, because y'all are astronomers.
I haven't.
I went up into the thumb with a friend a few nights ago. Weather report said 0 clouds. We get there, we look up, couldn't see anything. It was smoke from the fires on the West Coast. Couldn't even see Jupiter through the smoke.
Yeah, I don't know how many of you are like friends with Adrian Bradley of GLAC and now us on Facebook, but since he's an astro imager, he's been posting updates of the terrible, terrible conditions that have been plaguing him all week. So yes, the smoke from the West Coast has definitely impacted visual observing this week. Anybody else? Anybody seen any cool planet stuff? As you know, Jeff said, Saturn, Jupiter, Mars, Venus, everything is got its time slot.
So I don't have, I haven't done any observing, but I have bought some stuff on eBay, and I got a new eyepiece, which is a star guider, which has nothing to do with a star guiding telescope, 8mm eyepiece. And I've been using their 18mm and 25mm eyepieces for several years now, and have been, I got them at the swap meet for something like $25 a piece, and I've been tremendously happy with them and their performance. And I was helping a friend look for affordable eyepieces for his telescopes, for his new telescope, and I found these and found this 8mm that I haven't seen before. So I'm really excited to get to try it out on Mars, and I'll let you know if it performs as well as the other ones. The funny thing is, before I plonked down the $50 for this very nice looking eyepiece, I went and looked up reviews, and I found some extremely enthusiastic reviews of this whole line of eyepieces. And I got down to the bottom of the review and saw that it was signed by Steve Franks, who is a former WASP member and was a WASP mainstay for many years. So it is endorsed by WASP members.
What is the brand name?
It's Star Guider, which is a very confusing brand name. Agena is the major North American importer, but there's a company in Utah that is selling, apparently they're clearing out their stock of them on eBay, and they're selling they don't have the 25mm, which is my favorite, sadly, but they do have the 18mm, which is almost as good, for $50. And that I can wholeheartedly, I've spent a lot of hours with that one, and I can wholeheartedly recommend it. And for $50, you know, it's quite a steal. I mean, they perform as well as $80 or more eyepieces that I own.
Do you know what's the design?
It is, I mean, I think it's like
Orthoscopic?
something like a superplossil.
Okay.
But they also have twist-up eye cups, which is kind of neat. No more fumbling in the dark with the kind that spring up into your eyeball when you're trying to use them. So I quite like that too. Actually, Steve Franks may have commented more on the design on his reviews. But anyway, that's all I had.
All right. Any other observing reports? Aspirational observing reports?
I want to look at Mars. Mars last weekend. Was it last weekend or was it 2 weekends ago?
It was last weekend.
Was
2 weekends.
The
I mean,
best.
yeah.
It was the best that I've seen it, other than the summer of 2016. Because 2018 was closer, but it was, the dust storm started so early that I never got a halfway decent view. But it was just absolutely wonderful. So if you ever want to see Mars, make sure you see this. It'll be good through the end of the year, but it'll be especially good starting now until like the middle of November. So
Make sure you see it now before the dust storms kick up and we can't enjoy any of it is the thing, because 2016 and 2018 we had opposition dust storms. So yeah, look at Mars while you can. Okay,
What time does Mars rise?
it's rising in the evening. It is an all-night object, Jim.
Okay, thanks.
So, well, we have a little bit of time, or I can give y'all an extra break before our feature presentation. But does anybody want to ask an astronomer a question? Formerly known as Ask a Stupid Question, but there are no stupid questions. So, anybody have a question that they'd like one of our in-house experts in a particular subject to field?
I wouldn't mind just taking bets on the Venusian biome.
Taking bets, eh? You don't think it's caused by iron colliding with the nasty corrosives and just making a phosphine signature without any organic processes?
No, that's exactly what I think.
Oh, okay. So I'm not taking bets. We agree.
Yeah.
The bigger question with respect to the Venus thing is, what is life?
baby, don't hurt me. Oh no, that's love, not life.
We've been working on that one for a long time, and I think the longer we do, the more information that comes in, the farther we are from a real definition.
Well, even here on Earth, we've got viruses.
Yeah.
Right.
Well, I think we're excited about the idea of obvious life.
Yeah.
Hey, I'm excited about anything that happens on Venus, period. So
Okay.
I don't care what it is. I'll be happy about it.
Have you shared your postcard with everybody, Jonathan?
Oh, I haven't.
Jonathan got a birthday
Diane
present.
got me a post.
So I have an observing report.
All right.
So I tried a potential observing report. I tried to find the Minor Planet Ceres, the big asteroid.
Yep.
And I may have had it in my eyepiece in my lens, but I couldn't figure out which one it was. I guess it's too small, really, to observe more than the size of a small star.
But Uranus,
even
Ceres.
like a
Neptune,
magnification.
Ceres.
So. Yeah.
Oh yeah, no, it's just going to be a speck.
Yeah, it's a
Yeah,
speck.
I mean, honestly, you don't want to see an asteroid that isn't a speck.
But it's as big as Texas, right? So later on that night, I went over to Uranus and observed that and took some photos. I could see Triton, and I tried to see other moons, and I just couldn't. It was bouncing around too much. I took all my photos, averaged them together, got nice shiny blob, and sort of softened it up and processed it into a round image, and displayed some color from it. It's probably too processed, but whatever. I'll do another one and see if I can get some better viewing of it. But it was good to see Triton. My first time ever seeing Triton.
What equipment did you use to see Triton, Dale?
I have an 11-inch SCT, Celestron
Oh, okay, cool.
Edge HD.
Okay.
I think I was using either 2X PowerMate or the 2.5 PowerMate. I have both of them.
Cool.
I swap back and forth. Sometimes you're sort of chasing the scene, as like more magnification versus less light and timing. It actually seems to do better off with the 2x than the 2.5, but sensitivity in the camera and gain and all that kind of stuff. It's just a struggle for those outer planets. Uranus is coming up soon. That'll be a little easier. Last year I got 5 of the moons, and I'm hoping to get a little bit. I got definitely 4 and maybe the 5th moon last year. I think I can definitely get the 5 big ones this year. A little bit more experience about some.
So, Jonathan, before you show your postcard, Teresa Donnie has texted you a report since she can't give it from YouTube.
Oh. So she did. All right. So Therese says, I spent 5 beautiful days up at Port Sanilac, just north of the Thumb, and I gotta say, I could not believe the stars were beautiful every night. And I know I don't have pictures and I don't use a telescope, but we should not underrate naked eye observing on a beautiful night across Lake Huron every night I was out. So.
Good advice. Excellent advice.
And the new moon this morning was the outline, the earth shine of the new moon was really impressive. So if you haven't seen that, well, it might be too late, but it's still worth going after.
All right, Jonathan.
Another comment about the wildfires.
Yes.
So my wife and I were just out in Denver this week, and we were in Rocky Mountain National Park. They do have a wildfire north of there, and they had the through road closed for some days. It was open for us. I was surprised at how clear things were in the region until the last day when we drove back to the airport to come home, and we couldn't even see the front range. So it depends on like how the wind patterns and everything. So we left Tuesday morning, and the smoke had just obliterated the visibility to a couple of miles. So from Interstate 25, it's, I don't know, 30, 40 miles to the mountains, and you couldn't see them. So, but while we were there, to actually have a little bit of relaxation, the weather was actually kind and good to us. So, but I think that most of the fires are farther west.
Yes, Oregon, I think a bit of Idaho, up into Washington State. Yeah.
But I was looking at the smoke cover on an app, Astro. I have to look at it. And I messaged Doug Bach, and he said, well, the wind came down from the north and sort of pushed the smoke out. So up north right now, it's actually pretty clear. So
good.
Today's not as bad either. I might go out later on tonight.
Very good. Well, hopefully you'll come back with some great pictures come the next Cranbrook meeting, eh?
Maybe.
So, Jonathan, show your prize. We've got 2 minutes left before break time.
All right, so this is a vintage Venera Ochin. So you may remember this photo, in fact, from my presentation about missions to Venus. But this is an authentic 1975 postcard that is all, as you might expect, in Cyrillic. So, a Sokolo Venera Ochin na Venera. So it's just kind of a news update on what Venera 8 found on the planet Venus. So it's a very cool artifact, and Diane ordered it in like February or something, and it didn't show up until just before my birthday. So that was pretty cool. And what's really funny about the the person who sold it lives on Gagarina Street. So that was also kind of a funny thing, like Yuri Gagarin. So anyway, it was a very fun birthday present.
And I am very glad it arrived by your birthday because I thought the Russian post had done me dirty.
Jonathan, I wonder if the Russians are going to try and get an atmospheric sample on the next trip.
Well, if we'll see. Venera G is the G stands for long lasting, and it's taking a long time to even get out there. So right now the expected launch date is like the middle of the 2030s, and I wouldn't be surprised. I don't know if it's ever going to happen.
I mean, I would wait until we get rid of the coronavirus before we bring new microbes.
Yeah, that's a fair point.
Yeah.
What if the Venusian biome is exactly what will fight corona? This is the kind of frontier research we need to be doing.
There you go.
What the hell do you have to lose?
All right. And with that degeneration into memes, it is snack time. So take a 15-minute breather, grab your favorite drink, grab your Cheez-Its. We're out of Cheez-Its, and that is a crime. Bowl of apples, whatever. And we'll see you back here in 15 minutes for our feature presentation.
I have a question, kind of focused at you, Jonathan. Hey, John, you're still on there?
I'm here. If I'm the Jonathan to which you refer.
Oh, yes. So a friend asked for first-time telescope advice.
Mm-hmm.
I gave him some of my thoughts, but I'm kind of new too, and I'm more into photography than visual. And he didn't really give much specifics. He didn't give a budget. He didn't give what he was looking for. So I gave him a couple of options. But I wanted to ask you. You've mentioned these things in the past, and wanted to know if you actually use them. Celestron has a new one called Explorer DX, where it uses the cell phone to plate solve with a little mirror for the camera.
Yeah, so that's what my friend Amit got, and he's the very person that I recommended these eyepieces to. He was having some issues with it, and due to the coronavirus, I haven't really been able to meet up with him and try to work through them. So I don't know. What I read in reviews versus what he reports his experiences have been with the plate solving don't line up, and he hasn't been having the best time of it. It's a nice telescope. It comes with total garbage eyepieces, like really garbage eyepieces. They're like bad Kellners. But from what I read, that the primary is very nice. It's telescope generally.
Mount looks a bit chintzy, but it's a beginner scope. I don't know, maybe that's the norm.
Say that again.
The mount looked a bit chintzy, lightweight, but maybe that's the norm for cheap telescopes.
Yeah, is it? He's looking at the 130 or one of the smaller ones.
Yeah, well, I gave him some advice. I said, hey, take a look at this. It looks like it's pretty interesting technology for beginners. I've never tried one. Gave him the link. Actually, I gave him a link to a review on YouTube. And I also said, good aperture. A lot of people start with Dobsonian 6, 8, 10 inch. And that's a good way to get into it, but it can be a little bit harder finding stuff. That was that's kind of an issue for me, not knowing the night sky very well. It was harder for me to find stuff. Of course, I started out on SCT and, long focal length, so it's very hard to find little objects. Bad move. But I wasn't sure whether or not I would say number one recommendation would be a Dob or one of these star set things. I kind of like the idea, but yeah, does the implementation work?
I would say so. With those are super fast. They're super fast scopes. They're like f3 or I think they're like f4. And so I guess the big drawback to recommending them is that they're going to show you a big part of the sky, which is great. But if you're in a suburban, light polluted area, then that big chunk of the sky is going to be gray and kind of sickly looking. And if what they're really after is looking at Saturn and Jupiter and Mars, it can be a little bit underwhelming. And so, like, if you want to look at Saturn and Jupiter, Mars, the classic cheap refractor actually is really good at that. But for my observing, I go to dark skies a lot. I like looking at I like huge fields of view and low magnification, but I'm a little bit, I think I'm a little bit unusual in that regard. So it really depends on what your friend is looking for.
Yeah, maybe I'm going to hear back from him and maybe he'll focus it down, a budget or, what they're looking for. 14-year-old daughter just getting into it. Maybe they don't even know what they want to see. Start with.
Usually the thing is you generally don't know what you want to see until you've seen some of it. And I've known people who thought they wanted to get into galaxies and then became planetary people. I'm one of the few people who knew that they wanted to get into galaxies and has stayed into visual galaxy observing. It can be a somewhat it can be hard to keep the flame alive unless you get a stupidly gigantic telescope. Oh wait.
You did.
Yeah, I did.
Well, I don't know about stupidly, but it's sizable, right?
It's just the right size.
Okay, so to the group at large, is the sun white or yellow?
I mean, it's yellow, but it's effectively white.
I say white.
Well, fine then. You can say it if that makes you feel better.
Well, I mean, here's my logic. If the sun was yellow, then clouds would be yellow.
It's a good point. I mean, it's just so bright, though.
It's a point of confusion because isn't it classified as a G2 yellow star?
Yeah, but it's only very, very slightly yellow.
Yeah.
All right, Glenn, we have 13 people on the YouTube right now and 17 on the WebEx, so 30 people total right now.
What was the total we had the other night at the Cranbrook meeting?
We had 50 I think my suspicion is that we peaked at like 52 or 53 total for Cranbrook. But the Great Lakes Stargaze is on right now, and a few people have gone. So I think that's probably hurting our attendance tonight. Yeah. But I'm sure a lot of those people are going to catch up on YouTube during the daytime tomorrow.
I have another question, Jonathan.
Yes, sir.
I looked at the YouTube rebroadcast of the presentation of my presentation the other night, and I was again disappointed at the way music comes across.
Yeah,
I don't know if that's a bandwidth problem or if it's the computer or it's on the sending or the receiving end. Do you have any insight?
My suspicion is it's probably, it's probably a combination. I think it's quite likely that WebEx is intentionally filtering out wavelengths that it thinks might be background noise, and I think some of your guitar strums were getting somewhat filtered out. But I think also your microphone might not have been up to the task too.
Right.
So if you have like a USB microphone, or if you have a recording microphone and an adapter and a line-in jack on your computer or something like that, I bet we could make it work better. I'm hoping that by September next year we will be in person, but
Yeah.
we'll see.
Yeah, that would be certainly an improvement. Live stuff.
I was wondering whether when you started to play music, whether you got the guitar in front of you and backed up away from the microphone more and got to near the threshold of being loud enough.
Good question, but I don't know the answer.
Yeah, we might, we'll have to do a sound check next time.
Okay, good.
Like
Thanks.
a real rock sound check.
Okay.
Jonathan, with regard to the 25 millimeter star guider eyepiece, do you know what its apparent field of view is like?
I would say it's probably somewhere around 60% apparent field of view, 60-degree apparent field of view. It's a nice big, big image. I can fit. I think it's. I almost think it's comparable to. I feel like the field of view is almost similar to the field of view I get through my 2-inch 25 millimeter that I use also almost as much. So the two are two of my most used eyepieces, and they both have. I really like the field of view in both of them, but it's extremely wide for such an affordable eyepiece. So.
Is that from a company called BST?
Yes, that's the company in Utah that is selling them on eBay.
Okay. It's a 60-degree.
In honor of the Equinox. It's crossed the equator twice.
Say that again? 63?
It's a 60-degree.
60. Oh, wow, I was right. Cool.
I picked up a set of Meade HD 60s. I don't know that they make them. Actually, they might still make these. I don't think they sell them as a set anymore. I got it used on eBay with like the aluminum case and everything. I've only tried one of them. It's not as good as my larger, hand grenade sized eyepieces, but I thought I might might be good for traveling and taking them to star parties when those ever start up again.
Yeah, I definitely have a set of eyepieces that I use for the general public's eyeballs versus the ones that I use for my eyeballs and my friends' eyeballs. And at
Yeah.
Stargate, we have the same thing. We have the public outreach briefcases of eyepieces, and then the club member eyepieces. Although we do share hundreds of dollars of glass with the general public pretty frequently. So
Yeah.
All right, gang, we have hit the bottom of the hour.
When I was at the Stargate, someone had a Teleview Panoptic connected, and I thought that was, I didn't realize how good that was at the time.
Yeah. Gang, we've hit the bottom of the hour. It's 8:30, time to reconvene because we have, as Dale Parton said, a guest tonight that only the magic of the internet could have brought to us. So I would like to turn the meeting over to Dale to introduce our guest speaker.
Okay, thank you, Diane. This evening, it is my pleasure to introduce our speaker, Dr. Ryan MacDonald. He recently completed a doctorate in astronomy at the University of Cambridge in England. He's now a research associate at Cornell University's Carl Sagan Institute. At Cornell, Dr. MacDonald is developing new techniques to study exoplanet atmospheres in preparation for the upcoming launch, we hope, finally, of NASA's James Webb Space Telescope next year, I hope. His topic tonight will be revealing the nature of exoplanet atmospheres. Dr. MacDonald.
Thank you very much for that kind introduction, Dale. I will just find where I actually have the PowerPoint up. One moment. There we are. Okay, can you all see my screen?
Yes.
Okay, great. Well, let's get started then. So, we're truly in an extraordinary time when it comes to studies, not just of planets in our own solar system, but in terms of planets across our entire galaxy. It seems that almost on a weekly basis, there are new planets discovered, new strange things discovered in the atmospheres of these distant worlds. So it's certainly a very hot topic where a lot of breakthrough findings are coming about. And in my talk today, I'm going to be talking about some of the main ways that we currently use to characterize not just detecting exoplanets, but finding out what they are actually like. I will then present kind of some of the highlight studies and the incredible findings that we have identified to date before looking a little bit further into the future and look at some future prospects. So let's start with just a kind of quick recap of the current status of exoplanets which we have detected and how we find them. So the intriguing thing about the history of exoplanet science is that when you just look at our preconceived notions of what planetary systems should be like just from the solar system, exoplanets have kind of upended this from the very first discovery almost. So when we look at the solar system, we see we have 4 rocky planets close to the sun, and then the gas giants further out. So many of the early studies on how our solar system may have actually formed were all built on trying to explain why gas giants must form further out and rocky planets must form close to their star. So it was a surprise, suffice to say, when the first exoplanets, as we'll see in a moment, turned out to be gas giants orbiting closer than Mercury. But why is it hard to find exoplanets? Why haven't we known about them for hundreds of years, given that astronomical discoveries such as nearby galaxies and ideas on how the universe began have taken off for close to a century and many decades now? If you look at the nighttime sky and look at any star that you see, why can't we see planets around them? Well, if you just zoom into any particular star in the nighttime sky, the problem is that stars outshine any planets which are orbiting them by around a factor of 1 billion, and actually much lower than that if you are considering small planets like the Earth. So it's an incredible technological challenge to be able to tease apart planets just by looking at them directly, in the same way that we look at objects in our solar system or large extended objects in space like galaxies. So we've had to be more clever to infer the existence of exoplanets. So most of the early exoplanet detections, starting in the 1990s and into the 2000s, came from something that we call the radial velocity method. The essential idea is that instead of looking for the planet directly, we look at the light from the star, the spectrum of the star, and we see how, as a function of time, the light from the star changes. When the star is traveling towards us due to the gravitational pull of the planet, the light becomes slightly bluer, and when it is traveling away from us, the light shifts towards the red. And the size of this shift gives us some information on how massive the planet must be, because more massive planets have a greater gravitational tug on the star. So the first exoplanet discovery by the radial velocity method came in 1995. This wasn't the first exoplanet which was detected. That happened 3 years earlier in 1992 around a pulsar, but this was the first planet which was discovered around a sun-like star. And it immediately caused issues for our classical understanding of how planets form, because here was a gas giant orbiting 7 times closer than Mercury on actually just a 4-day orbit. So it couldn't have formed here according to our classical theories, and due to much theoretical work that came in the years to follow, we now believe that so-called hot Jupiters like this originally formed far out in the disk and then migrated inwards during the evolution of the disk that planets form from. So, and this planet was also the basis of the Nobel Prize in Physics, which was awarded last year. So the instruments that were used to detect planets like 51 Pegasi b improved dramatically over the following 10 years, getting down to the sensitivity where in the early 2000s, it was possible to start detecting rocky planets around other stars. So here is an illustration of the first of an object that we now call super-Earths, which are rocky planets which have a greater mass or a greater radius than the Earth. And it was actually only just a few years after that that we started for the first time finding planets which were around the right distance from their star, that hypothetically they could support liquid water on their surface, which is what we mean by the habitable zone. But the true revolution in exoplanet detection, so up to this point only a couple hundred planets had been discovered, came in 2009 with the launch of NASA's Kepler Space Telescope. Kepler looked for planets using an entirely different technique called the transit method. It essentially just stared at 150,000 stars, watching for telltale dips in the light the stars emit as a planet passes in front of it. Where the size of the dip, the amount of the light blocked by the planet, tells us the radius of the planet. So just a few years after Kepler launched, it started producing hundreds and then even thousands of exoplanet discoveries, including for the first time planets around about the size of the Earth orbiting in the habitable zone of other stars. And here I'm just highlighting some of the big discoveries. But perhaps one of the most dramatic discoveries of planets that would potentially have habitable conditions was reported a few years ago. It was the discovery of Proxima Centauri b, an exoplanet around the nearest star to us in the nighttime sky, Proxima Centauri, which is about 4.2 light years away. And here was a roughly Earth-mass planet lying in the habitable zone of the nearest star. Our early dreams from science fiction could not have been more pleased to see this, and if indeed one day we do eventually develop the technology to go to nearby star systems, Proxima b would probably be one of the first destinations to consider. And one discovery that occupies a lot of my time these days was the discovery of the TRAPPIST-1 system. So this is a collection of 7 rocky planets around 40 light years away, orbiting a small M-dwarf star, with 3 of these planets at around the right distance to reside in the habitable zone. So the takeaway from these early exoplanet discoveries, is that planets are not only common in our galaxy, there's around about 1 planet per star on average, but rocky planets residing in the habitable zone of star systems are quite common. Around 1 in 4 is the frequency that we have inferred. And in fact, just yesterday, a discovery which I'll talk a little bit more about later was announced, because it has some interesting implications for the search for life in the universe, was the discovery of the first transiting exoplanet around a white dwarf, the residual core of a long dead star, WD1856b, which is a very exotic system and the first of its kind. So this is just to illustrate the point I was saying earlier, that new planet discoveries of strange new systems are coming out all of the time. So in fact, if we chart how many planets we have known as a function of time from the 1700s to the present day, you'll suddenly notice, once we get into the 1990s, a huge uptick in the number of planets we are aware of. So here are the radial velocity planets just coming in the 90s and 2000s, and watch out for 2009, when Kepler launches. All of a sudden, it dumps a huge number of transiting planets, and although this animation only goes up to 2018, the latest count is over 4,200 planets have been discovered, with NASA's TESS mission currently doing a survey of the entire sky, looking for many thousands of new worlds around nearby bright stars. So this plot that I'm showing here is just comparing the diversity of the worlds which we have discovered to date to the planets that we're all familiar with in our own solar system. So the plot on the left is showing the mass of the planet versus how far away from the star the planet orbits, and the one on the right is the size of the planet, and as a function of how long its year is. So we can already notice that there appear to be 3 distinct classes of planets that we have discovered. So we have found planets like Jupiter, gas giants orbiting far away from their star. We call these objects now the cool Jupiters, which are a different class of objects from the hot Jupiters, which we don't have in our own solar system, and were some of the first planets that were discovered. So these are roughly Jupiter mass, Jupiter radius objects, but taking on the order of a few days, not years, to orbit their star. And a third class of objects are what we call the subgiants, which includes rocky planets, super-Earths, and roughly Neptune-sized objects. There doesn't appear to be any clear boundary that we see between Neptune mass planets and rocky planets. There appears to be a continuum spanning these objects. And this plot is just illustrating what you can do if you know both the mass and the radius of a planet. So if you can detect the same planet using the radial velocity method to get a mass and the transit method to get a radius, you can then start to tease out some details on what the planet is made of. So most of the planets we have discovered so far lie close to Jupiter and Saturn on this plot, the S and J stars that you see there. They are massive objects with large radii and are hence consistent with being made of hydrogen and helium. But we have found some exoplanets which are close to the radius and the mass of the Earth. So these would be terrestrial planets. So the 7 kind of blue dots that you see near Earth and Venus in the bottom left there are the TRAPPIST-1 planets that I mentioned. The colours here are denoting the temperature of the planet. So you see we have even found some planets that appear to be rocky, but with temperatures of many thousands of degrees. And these are what we call lava worlds. So if you know the mass and radius of a planet, that already gives you some information on what the planet is made of. But if we really want to know what these worlds are actually like, we need to turn to studies of the atmospheres of these planets. Because if an alien astronomer were to look at our own solar system, from the mass and radius, you wouldn't be able to tell Venus and Earth apart. They're very similar in terms of those two characteristics. So the atmosphere is where we can really learn about these planets. So I will be discussing the 5 techniques that we use to characterize exoplanet atmospheres. The most successful technique, which is the one that I work on principally, involves teasing out information about the planet's atmosphere during the transit when it passes in front of the star. But there is also information that you can learn from looking at the eclipse when it goes behind the star, and also by looking at how the light emitted or reflected by the planet changes as it travels around its star. So we'll look at each of these techniques in turn, starting with the transit. So the essential idea here is to go beyond just trying to measure the size of a planet. The key idea is that during a transit, some of the light from the star will pass through the atmosphere of the planet. And because of the various gases that make up the atmosphere, absorb different wavelengths or colors of light differently, some colors of light will be absorbed by the atmosphere, while others will just pass through entirely unhindered. So what this means in practice is that the size of the planet during transit changes as a function of the wavelength of light that we observe. So at a wavelength where a particular molecule in the atmosphere absorbs strongly, like shown by the orange curve here, the planet will appear to be slightly larger. It absorbs more light. So by building a plot of how the size of the planet changes as a function of wavelength, and comparing that to laboratory measurements that we have from the Earth of where each molecule absorbs, we can back out what the chemical composition of the atmosphere is made of. And what still amazes me about this is we can't spatially resolve the transit like we see here. All we're doing is looking at how the light from the star changes as a function of time and color. So the fact that we can indirectly measure the chemical composition of a world we can't even see is quite extraordinary. So to kind of make this a bit more precise, I put together a little cartoon here that shows the main features of what we call a transmission spectrum. So the amount of light blocked as a function of color. So if you had a planet which has no atmosphere, which is just a rock doesn't care if you have blue light or red light, it will just block all of them equally. So we will just have a flat curve like seen here on the right. If you now add a large atmosphere made of hydrogen, for example, hydrogen doesn't absorb light at many particular colors, at least molecular hydrogen, but what it does do is it scatters light. And in fact, light at very blue colors or high energies tends to kind of be absorbed and re-emitted. So for the same way that the Earth's atmosphere is blue due to light being scattered in all directions, some of the light gets scattered and misses our telescope. So the planet appears to be slightly larger towards the blue wavelengths. For hot gas giant planets, like hot Jupiters, which can be thousands of degrees, we expect there to be atomic alkali metals, so sodium and potassium in their atmospheres. And these have characteristic colors. So if you've ever seen a sodium street lamp, for example, they have a characteristic orange color, which corresponds to the wavelength of one of the electronic transitions in the atom. So if we see the planet suddenly appear to be brighter at a precise wavelength where light is orange, we can tell that there is sodium in the atmosphere. And there is a similar transition caused by potassium just towards the red end of what we can see with our eyes. But if we extend this to longer wavelengths out into the infrared, then we can start to access molecular features. So when molecules absorb light, most often electrons aren't being excited, what is happening is molecules absorb some of the light and then start rotating, or they start vibrating about their bonds. And the energy that causes these vibrations or rotations to start occur in the infrared. And in particular, some of our most successful observations of exoplanet atmospheres to date have come from an instrument aboard Hubble, which was installed on the 2009 final Space Shuttle servicing mission. So that mission was quite vital to almost all of the findings that I'll talk about today, especially for knowing that there is water in exoplanet atmospheres. So here's my cartoon sketch. I'll just skip over that for now. This is what real data of an exoplanet atmosphere seen by Hubble looks like. So the orange points here are showing how the amount of light absorbed by a planet changes as a function of wavelength, and the absorption suddenly increases at this wavelength, around 1.4 microns, which is a characteristic absorption feature due to water, shown in this red model here. So the first exoplanet that we detected the atmosphere of is this world with this very easy to remember telephone number, HD209458b, sometimes also unofficially known as Osiris. So sodium was detected in this atmosphere in 2002, which was the first time we detected an exoplanet atmosphere. And many additional molecules have been discovered since. So we have found water, we have found evidence of clouds, and even potentially some of the building blocks of life, ammonia and hydrogen cyanide, even though planets like this certainly would not be an hospitable location for life. And on the right here, I'm just showing a diagram showing kind of the state of the art at the moment when it comes to observations of exoplanet atmospheres. The point to make here is that the observations we currently have are not great. There are very large error bars here, and that's because we're using instruments that were not designed to study the atmospheres of planets around other stars. So the Hubble Space Telescope was launched before we even knew that planets around other stars existed, and it's only now that we're starting to design new generations of instruments specialized to do this work. But that being said, we have reached a point where we've studied around 50 exoplanet atmospheres to date, and we have around a dozen planets with secure detections of water vapor in their atmospheres. So that's the transit method, which is the most successful one to date. Let's take a look at what we can learn from looking at when the planet goes behind its parent star, the eclipse. So just before the planet goes behind its star, the light that falls into our telescope contains the light from the star and the light which is being either reflected or emitted from the day side of the planet. So by comparing the total planet plus star emission before the eclipse and during the eclipse, where we only see the starlight, we can infer what the properties of the day side of the planet is like. So this cartoon here is showing that if we have a planet where it gets colder as you go higher in the atmosphere, which is like the blue curve in this plot right in the middle. And there is a layer in the upper atmosphere of molecules that strongly absorb light, like these water molecules here. When you look at a wavelength where water absorbs strongly, you will be probing the upper atmosphere. But if you look at a wavelength where the water molecule is transparent, you can see deeper in the atmosphere. So what this means is that at different wavelengths, the amount of flux or emission from the planet will be higher at corresponding to altitudes of the planet where it's hotter. So by looking at how the flux from the planet or the thermal emission changes with wavelength, we can infer some information as to whether the temperature of the planet gets colder at higher altitudes or whether it increases. So for example, on Earth's atmosphere, once you go up into the stratosphere, the Earth's atmosphere gets warmer due to ozone absorbing ultraviolet radiation from the sun. So if we can infer that a planet warms up in the upper atmosphere, that can tell us that there must be a molecule present in the atmosphere that is strongly absorbing ultraviolet light. And this would be important, for example, for future studies of the habitability of worlds. And this is just illustrating here a recent finding that shows that, at least for gas giants, which is what we can mainly study today, we are already finding planets which appear to have these hot extended stratospheres, so upper atmospheres strongly absorbing light. For this particular planet, called WASP-121b, this isn't caused by ozone. This is caused, we believe, by an exotic molecule called vanadium oxide, which is a molecule that we don't even see in the planets orbiting our own solar system because they aren't hot enough. We do see it in the atmospheres of cool stars. So the chemistry of these objects is quite distinct from what we have in our own solar system. The third technique is called looking at the phase curve. So if you think, for example, about phases of the moon or phases of Venus, the same idea is true here. By measuring the amount of thermal emission or reflected light from the planet as it orbits around the star, I should say all of these planets are orbiting close enough that the gravitational tug of the star should cause them to be tidally locked, like our own moon. So they will have a permanent day side and a permanent night side. And as a consequence of this, during the transit, we are observing the night side of the planet because the planet is facing towards the star. But half an orbit later, the day side rotates into view just before the secondary eclipse. And if you look, say, halfway between the transit and the eclipse, you're then probing half of the day side and half of the night side. So as a consequence, the total amount of light we receive from the system increases just before the eclipse because we are seeing a thermal contribution or a reflected light contribution from the day side of the planet on top of the light from the star. And the really exciting idea here is that because we are observing different hemispheres as a function of time, if we have precise enough observations, we can produce a low-resolution, spatially resolved map of the temperature distribution of a planet. So this is, again, we can't see the planet directly, but we can map out how the planet's temperature changes with longitude. So this is the first such thermal map of an exoplanet from another hot Jupiter, published in 2007. And the interesting thing here is that, so the sun-facing longitude here at 0 degrees is the center of the day side of the planet. So you might expect that the hottest part of the planet would be smack bang in the middle of the day side. But instead we see it is offset by around 30 degrees longitude. So this is actually evidence that these hot exoplanets have strong winds which transport energy around the planet from the day side to the night side. So the hottest part is offset because of winds blowing at many kilometers per second on these objects. And this animation is just illustrating how the amount of light changes as a function of time as we probe different hemispheres of the planet. This has even been done for a super Earth. So this is actually one of the worlds I spoke about earlier. It's the first super Earth which was discovered, the so-called lava world 55 Cancri E. And this is probably the worst map that you have ever seen for an entire planet. It's so hard to do these measurements. So you can only really resolve it in this case to around a width of about 60 degrees in longitude. But the point here is that the hottest part of this planet at about 3000 degrees Celsius, is also offset from the center of the day side. So it has been speculated that what we're seeing here is a lava world where the motion of magma around the surface of the planet is carrying some of the heat towards the east. The fourth technique out of the 5, which lets us actually learn something about planets which don't even transit, which has been the case for the previous 3 techniques, is called high-resolution Doppler spectroscopy. So the idea is that if we observe a system, even with a non-transiting planet, as a function of time, and we look at it with a very, very high-resolution instrument, high resolution in this case isn't the spatial resolution or magnification, but the wavelength resolution. So we can chop up the light into very, very, very tiny, narrow regions. What we expect to see is light reflected or emitted from the planet should vary as a function of time, because the planet is changing by many kilometers per second in its orbital speed. And so that should cause redshifts and blue shifts, not just in the starlight, but in the light reflected or emitted from the planet's atmosphere. So in this diagram down at the bottom, the white lines here are showing how absorption lines from the molecule carbon monoxide would change as a function of time as they are redshifted and blue shifted. So this technique has been an extraordinary success. For example, just a few years ago, it was used to detect water vapor in the atmosphere of the first hot Jupiter, 51 Pegasi b, even though this planet does not actually transit. It has also been used to probe the atmosphere of an extreme class of objects that we now call ultra-hot Jupiters. So these are objects where the temperatures are in excess of 2000 degrees. This object, Celt 9b, shown in this artist concept, is the hottest exoplanet we know. Its day side is actually hotter than some cool stars, around 4000 degrees. And so it was predicted that we should see ionized metals in the atmosphere of the day side of this planet, which were reported 2 years ago. So iron and ionized iron, alongside ionized titanium, was found in the day side atmosphere of this planet. So you can imagine this as a world where it's almost half planet and half star, a day side with a stellar atmosphere and a night side with molecular features. So a very strange and exotic object. And the final technique for studying exoplanet atmospheres is something that I alluded to right at the beginning of my talk when talking about how difficult it would be to directly see an exoplanet. So, and I think someone is unmuted. Not sure if you have a question or if you're unmuted, but I will continue. So if you can use a device called a coronagraph to block out or subtract some of the light from a star, it is possible with sufficiently advanced instrumentation and a large enough collecting area to see planets which are quite far out from their star. So we don't currently have the technology to do this for Earth-like planets or even for planets as far out as Jupiter, but we can imagine, for example, a Jupiter-sized planet which is incredibly hot because it's only a few hundreds of millions of years old, but is orbiting about as far out as Neptune. That's about where we are at the moment with current technology. So, for example, this system here, which has a striking resemblance to something you might recognize, is called the Fomalhaut system, which was one of the first claimed directly imaged exoplanets. So there is a tiny little pinprick of light here that, I forget the distance, but it's many hundreds of astronomical units, I believe, that was one of the first claimed directly imaged exoplanets. But, I mean, here is also an animation kind of showing some of the evidence for this. But to illustrate how hard this is, just earlier this year, it was reported that this planet appears to have magically disappeared. These are not actual observations here. This is a model to try and explain it. So it's possible that this is not even a planet, but it's a speck of dust that we mistook as a planet. But that being said, we have actually found some planets that we still believe are planets via direct imaging. So, and that was just my explanation for where the planet has gone. So this absolutely amazes me. This is not a model. These are an actual series of observations taken over many years of a multi-planet system where we can actually see 4 exoplanets orbiting around a star. So for scale here, this is 20 astronomical units. So Pluto is at 40 AU. So you see that some of these, well, actually probably these outer 3 most planets are orbiting as far out or further out than Pluto is. So it's hard to make these measurements, but it is possible to directly see some exoplanets. So how this helps us with atmospheric studies is that if we look at how the amount of light from the planet changes as a function of wavelength, at wavelengths where the planet appears to be slightly dimmer, that is telling us there must be a molecule in the atmosphere, such as water or methane in this case, absorbing the atmosphere, absorbing the thermal emission from the planet. So direct imaging is essentially how we started studying Jupiter and Saturn in our own solar system in the early 1900s, before the dawn of the space age. So it is quite humbling that where we are for exoplanet atmosphere studies at the moment is kind of commensurate to where we were in the 1920s for studies of the planets in our own solar system. So we're just making we're doing the very initial reconnaissance to figure out just what the atmospheres are even made of. Right, so now that we've looked at the 5 methods that we use to peer into the atmospheres of these planets, in the remainder of my talk, I'm going to look at some actual discoveries. And I'll start with a case study from a few years ago of some work that I did looking at the atmosphere of a hot Jupiter. So let's depart on our spaceship of the mind and head on over to the WASP-19 system, which has a very interesting planet orbiting around it. So WASP-19 is in the constellation of Vela. It's 815 light years away, a roughly Sun-like G-type star. And the exciting thing about this system is that we've known for a while that it has a hot Jupiter with a very large extended atmosphere because it orbits so close to its star. It just has a 19-hour orbit that its predicted temperature should be around 2000 degrees Celsius. So the reason that the vast majority of planets that we have characterized to date are hot gas giants is simply because the hotter the planet is, the more extended its atmosphere is, and so the more light is obscured by the atmosphere during transit. So it makes it much easier using telescopes like Hubble to detect the faint signal of the planet's atmosphere. So using instruments aboard the Very Large Telescope Array down in Chile, some of my collaborators obtained a transmission spectrum which looks like this. So this is the fraction of light absorbed by the planet in percentage as a function of the colors of light that we can see. So this is colored intentionally, so kind of blue light, green light, and red light. And just by eye in the data here, it looks like there are some kind of wiggles. So you can tell just by eye there must be something in the atmosphere absorbing different colors of light. So during my PhD in Cambridge, I spent a long time working on trying to come up with theoretical models that could explain what this atmosphere was made of. Because in particular, we had never seen this absorption feature here. So it required us to be a bit creative with our modeling. The answer that we found is that these features here can be beautifully explained by a metal oxide, the molecule titanium oxide, which is a molecule that is sometimes seen in the atmosphere of cool red dwarf stars, but has never been seen before this point in the atmosphere of an exoplanet. So we also found sodium and water, but this was quite exciting because this was the first detection of titanium oxide in the atmosphere of a planet. And we were even able to place some loose measurements on how much of each molecule there is in the atmosphere. So roughly 1 molecule in every 10,000 is water in the atmosphere, 1 in a million is sodium, and about 1 in every 10 billion is titanium oxide. So this is a trace species, but it absorbs very strongly. And titanium oxide is actually one of the species that we believe can cause these stratospheres, so layers in the upper atmosphere that strongly absorb light from the star, as illustrated here in the case of Earth, where ozone is what causes a stratospheric increase in temperature. Okay, so let's move on to the future, and particularly to prospects of studying terrestrial or rocky planets. Because where we are at the moment has been very much focused on studies of giant exoplanets, just simply because the telescopes that we currently have don't have a large enough collecting area or sensitivity to peer into the atmospheres of planets like Earth. But that will change very soon. So this is kind of just illustrating the progression in atmospheric studies. So we've been studying stars for centuries. Hubble has helped us unlock brown dwarf atmospheres, hot Jupiters, and we have atmospheric measurements for around about 5 planets the size and mass of Neptune. But if we want to push into the regime of studying the atmospheres of super-Earths and terrestrial planets like the Earth, for that we will turn to the James Webb Space Telescope, which hopefully will finally launch next year. So James Webb will be our first chance to observationally probe the atmospheres of potentially habitable planets around nearby stars. And in particular, what we will be focusing on will be rocky planets around red dwarf or M dwarf stars, because these planets have habitable zones which are much closer to their star due to the lower temperature of the star, which actually increases the probability of a planet transiting if it's orbiting closer to its star, and it means that these transit events happen much more frequently. So instead of having to wait a year for every transit like alien astronomers would have to do to study the Earth, the habitable zone for planets like Proxima Centauri b places these planets on orbits of around about a week or so. So it's much quicker to collect the observations for these planets. So here is some simulations that I've made of one of the best targets that we currently have. This planet TRAPPIST-1e, which is the 4th planet out from the star TRAPPIST-1, which is that system I mentioned earlier with 7 rocky planets. So these simulated observations are for what TRAPPIST-1's spectrum would look like if you observed 100 transits with the James Webb Space Telescope and the atmosphere was the same as what we have on the Earth. The key takeaway here is that we can readily detect molecules like water and carbon dioxide, and we can, even if we have enough observing time with the telescope, tease out the small signatures due to biosignature gases, so things like methane, ozone, and nitrous oxide. But even with the extraordinary power of James Webb, this will take a long time. This represents around 5 years of observations with James Webb. Not all in one go. You don't have to stare at it for 5 years. You would just need to look once every week or so whenever the planet transits. But still, this would be an extraordinary investment in telescope time. So if we only study planets around red dwarf stars with James Webb, we will be lucky to look at a handful of planets, on the order perhaps of 5 planets over the lifetime of the mission. So I've been interested in whether there might be a better way to look for biosignatures, which is much faster. So yesterday, I published a paper suggesting a new way to look for signs of life around exoplanets in a companion paper to the discovery of the first planet around a white dwarf, which was also published yesterday. So our idea is that if we can find Earth-sized planets orbiting white dwarfs, the leftover cores of stars like our Sun, white dwarfs are so small that they're only actually slightly larger than the size of the Earth. So during a transit event, around half of the light from the white dwarf would be blocked by the planet. And this means that the fraction of the star's surface covered by the atmosphere will be much greater, and hence the signatures of the atmosphere will be much stronger even than the signatures from red dwarf stars. So if we can discover a rocky planet orbiting a white dwarf, which we haven't found yet, but we are undertaking surveys now to look for, our new paper suggests that instead of waiting 5 years to find biosignatures, with James Webb, in just a 2-week observing campaign, we could find signatures of gases like ozone in combination with methane, which is one of the strongest signatures of life in the Earth's atmosphere. So we believe that our best bet to find life in the universe, at least beyond our own solar system, in the immediate future, will be to look for planets around white dwarfs. So fingers crossed they actually exist. James Webb will not be the end of the story, though. In the middle of this decade, a new generation of extremely large ground-based telescopes will be coming online. So the European Extremely Large Telescope in Chile should see first light around 2025. This will have a 40-meter primary. So here's a car and here's a truck in the bottom left corner here for comparison. This telescope is extraordinarily large. So the Extremely Large Telescope will be sensitive enough that by using high-resolution spectroscopy, it would be able to detect signatures of oxygen in the atmospheres of non-transiting planets. So, for example, the planet Proxima Centauri b potentially would be within the realm of detectability for oxygen if it has an Earth-like atmosphere. So, given when the telescope will see first light and the amount of time to collect the observations, perhaps you're looking at around the year 2030 for studies of molecular oxygen as a biosignature for nearby rocky planets. The European Space Agency will be launching a mission towards the end of this decade, Ariel, which will be the first dedicated space mission to study the atmospheres of exoplanets. So we don't at the moment have any dedicated telescopes that can do this. So we have to write proposals for Hubble time. And so over the course of the last 2 decades that we have been doing this, we've looked at 50 planets. Ariel, as a dedicated mission, will do a survey of around 1,000 exoplanet atmospheres, showing the true atmospheric diversity of the chemical composition of nearby planets in our galaxy. Slightly further afield, in the 2030s and 2040s, a notional successor to the James Webb Space Telescope, LUVOIR, which is currently being studied as a potential flagship mission around the 2035 timeframe, would be sensitive enough to directly image a true Earth twin analog. So for a size comparison, here is how LUVOIR would potentially compare to the primary of Hubble and of James Webb. So this would be an extraordinarily ambitious mission, and the decadal survey process that NASA is going through at the moment will potentially decide whether LUVOIR is what NASA wants to focus on in the decades to come. And the last parting thought that I will leave you with is potentially the prospect of visiting an exoplanet in the far future. So one initiative that has been proposed to do this is called Breakthrough Starshot. The idea would be to miniaturize a probe down to around 1 gram attached to a solar sail and to illuminate it with laser irradiation to use photon momentum to accelerate these tiny microprobes up to 20% of the speed of light. And at such a velocity, we could send a small probe to the nearest stars, taking around 20 years to reach, say, the Alpha Centauri system. So the technology is not yet there to do it, but the Breakthrough Foundation is funding a lot of theoretical engineering work at the moment to try and lay the groundwork for this. So if sufficient funding were available to do this, a mission like this could launch around the 2040 timeframe, and we could potentially have the first photos of an exoplanet around 2060. So this simulation here is showing what one of these probes would actually see in real time if it were to do a flyby of the exoplanet Proxima Centauri b. So we will see in a few short moments precisely how long you would have to get photos after a 20-year journey to this nearby system. Here we go, and snap, 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 snap. Okay, there's your flyby done. That's all your photos, and then it will take another 4 years to get the data back to Earth. But still, the tantalizing idea that we could be with just a few decades away from actually visiting an exoplanet, it's incredible to see how rapidly this field is moving. So that is my parting thought on some of the potential progressions for this field. And with that, I would be happy to take any questions that you might have.
Fabulous. Yes, we have a good 8 to 10 minutes for questions to follow up on this wonderful talk. Let's go, gang.
I have a question. The James Webb Telescope is going to be oriented basically toward infrared. My impression is that if it had also had the capability to do ultraviolet, it would be much easier to detect molecular oxygen or ozone in planetary atmospheres. Is that correct? And I assume it's, with all of the delays the mission has had, I assume it's too late to add that capability.
Yeah. So James Webb can observe down to around 600 nanometers. So it can do roughly like the kind of the end part of the visible spectrum. But yes, it is mostly infrared. So you're absolutely right about the difficulty in studying oxygen and ozone. So ozone in particular has a strong absorption feature in the near UV at around 250 nanometers, which can't be accessed by James Webb. So we're really hoping that Hubble will stick it out for a little bit longer so that we can do simultaneous observations with the UV capabilities of Hubble and James Webb. So yeah, that is really a pity. LUVOIR would have both UV, optical, and infrared capabilities. But yes, so far too late in the process to add UV capabilities to James Webb. That being said, ozone does have an absorption feature in the infrared, at around 10 microns that you could target.
All right, next.
Go ahead, Jim. Jim, you're muted. Jim, you're muted.
Oh, okay, thank you. I was trying to unmute it with the little icon on my postage stamp. Question, will the Giant Magellan Telescope have any role in the search?
That's a great question. So I'll admit I don't actually know the answer to that question. Most of my focus has been on James Webb and ground-based telescopes like the VLT and the ELT. But I would be surprised if it does not have spectral instruments that can do that. So my suspicion is yes, but I don't know the specifics.
I have a slightly offbeat question. When it was announced that there might be a planetary system around Fomalhaut, that was a bit of a head scratcher for a lot of us amateurs. It kind of didn't make sense. What was your reaction when the preliminary news was announced that it was thought to have a planetary system?
Oh, that. So the funny thing here is when that was announced in, what was it, 2006 or so. I was in the school like when it was announced. So that was quite a while back. So I actually didn't hear about the discovery because we've only really upped our outreach initiatives in exoplanets, especially since Kepler launched, and I've been trying to really do a better job on that front. So I didn't have any reactions because I didn't know actually that the system was discovered. But whenever these directly imaged planet discoveries are made, especially when we see these animations, I'm just amazed that we can see actual planets around other stars. It's only a matter of time that we follow until we follow the logical progression in the words of Carl Sagan to see pale blue dots around other stars. And indeed, some of the direct photographs that we see of giant planets around other stars do even have a kind of subtle blue tinge to them. So yeah, I'm just continually amazed that we can even make these measurements.
So am I correct in thinking that you are a theoretician more than an experimentalist?
Yeah, that's correct. I kind of straddle the boundary between theory and observation. So I create theoretical models of the atmospheres of these planets, but it's all oriented around trying to explain observations that we have with Hubble and James Webb. So most of the work that I've been doing at the moment is looking at the amount of observing time that we would need with telescopes to detect various molecules in the atmospheres. So that informs writing proposals for telescopes, and especially, for example, when it comes to things like the announcement we saw earlier this week of phosphine potentially in Venus's atmosphere, we use theoretical models of exoplanet atmospheres to study whether you could detect molecules like phosphine and how many hours it would take. So yeah, I try and keep rooted in both theory and observations because that's the sweet spot where we actually make discoveries about what these worlds are actually like.
So would you care to hazard an opinion on whether phosphine on Venus is from life?
Well, I should say first that I think more work needs to be done to secure the detection of phosphine first, because the evidence so far is just one spectral line. And when we look at exoplanets, like you would never claim a detection of a molecule just from a single spectral line. So I would like to see observations of different transitions of the phosphine molecule at a different wavelength region, just to really be sure that it's phosphine, since it's such an extraordinary claim. And I believe next month, actually, the Bepi-Colombo mission is going to do a flyby of Venus. And there'll be another flyby next year. So the science team will look to see if they can potentially use some of those instruments to verify the claim of phosphine. So I would take it one step at a time. Check that the phosphine is there to start with, before you start speculating about the potential presence of life. But I hope that it is life. I mean, that's what gets most of us exoplanet astronomers into the field, these big picture questions of whether there is life in the universe. So if phosphine is there, it's very hard to explain abiotically. But yeah, I'm still a little bit skeptical about whether or not the phosphine is actually there.
You know the temperature at the cloud top of Venus? Do we know the temperatures at the cloud tops of Venus? We know them?
Reasonably tolerable
Okay.
compared to the temperature anywhere else on Venus.
Yeah, when you look at, I mean, in the 60s, like Carl Sagan had a paper talking about how there is this region near the cloud tops of Venus where you essentially have habitable by Earth standard conditions. So in terms of the temperature and pressure, obviously there's not oxygen in the atmosphere, and there's the minor issue of sulfuric acid, which would melt you. But besides those minor detractions of it as a destination to go to, the upper atmosphere of Venus is surprisingly tolerable.
Yeah, okay. This is great.
So, Dr. MacDonald, if I could ask a question that is not directly related to this, your direct presentation subject, but is related to your presentation to us. You said that the professional astronomy community wasn't doing the best job with public outreach back in the mid 2000s, and I would agree with that. I feel like I encounter a lot of professional science communicators on the internet these days. Is that an area that you spend a lot of time, trying to develop our community, and which I think is good for everybody, both the general public and the funding prospects of researchers?
Yeah, absolutely. So, I mean, my philosophy is that the job of us as scientists doesn't stop just when we publish a paper, especially given that most of the research we do is funded by the public. We have a duty to communicate the wonders of the universe that we have discovered, and not just keep it all to ourselves. So the discovery process and making sure the science is right is crucial, but the communication aspect, and personally, it's one of the things I enjoy most as a scientist, getting to share all these wonderful findings. But I would argue that it's improved a lot in recent decades, especially with the internet making it easier. So, for example, I have my own YouTube channel where I make videos about planetary science, exoplanets, and a lot of videos about Mars, because human missions to Mars is a hobby interest of mine. And I will actually be releasing, probably in a few hours, a half-an-hour mini documentary on my YouTube channel specifically about the search for life on planets around white dwarfs, based on the paper that I released yesterday. So yeah, I try and do my part on the outreach front, and also at Cornell, for example, I'm also training up other astronomers in how to make videos, for example. So yeah, outreach is a critical part of the job that we do.
On that point, would you care to tell people the website where you place these things?
Yep. So my YouTube channel is called Martian Colonist, because it was originally about sending people to Mars. So yeah, you can find that on YouTube, just youtube.com/Martian Colonist. And for general background on my research, you can look at distantworlds.space.
Awesome. Awesome. Any other questions? Anything coming in from YouTube, Jonathan?
I don't see anything. I almost let me pop over to the real YouTube because it's been unusually quiet and there are 15 people on still. So let me double check.
Certainly.
In the
Maybe
meantime,
while Jonathan is doing that, I'll ask another question. By the way, this is Dale Parton, who we've communicated with you. Would you care to speculate on what might happen? And I realize this is not exactly in your field, okay? Suppose we send astronauts to Mars and there's life there. How much do we have to worry about that life infecting them with something deadly and they're bringing it back to Earth?
Well, planetary protection is taken very seriously. So, and it's a double way process. So it's not just about sterilizing the missions that we send to Mars, but back contamination is treated very seriously. So the discussions about, for example, the Martian sample return, which potentially could be one of the outcomes of the second part of the Perseverance mission, for bringing things back for study on the Earth, could potentially inform the risk of. I mean, I don't think it's likely that there are microorganisms on Mars which are, either A, compatible, or B, sophisticated enough to infect us, if you will. I mean, it's a great science fiction story about strange viruses in water on Mars, for example. So it's fun to think about, but it's probably unlikely based on what we know at the moment. Well, I mean, that being said, the story of science is a continual story of surprises. I mean, who would have thought last week that we would now potentially be thinking that Venus could be one of the best places to look for life? So when it comes to astrobiology, I don't rule anything out, because I think we should try and have an open mind. But that being said, I hope there aren't any strange viruses on Mars that can infect us. But so long as we're not shipping loads of material back from Mars to the Earth, yeah, that shouldn't be much of a concern.
Thank you.
I
Excellent.
didn't find anything on YouTube, although I'm getting texts from people who are watching on YouTube that it was a great presentation. So
It certainly was. Well, it's 9:36, so thank you so much for joining us tonight. Really glad we had the opportunity. Thank you to Dale for lining this up. I wish we could take you out to dinner as we normally would for a guest speaker, but
And thank you very much.
2020. Thank you.
John, can you give me some participant information?
I think we topped out at around 36 people total.
I think you said 15 on YouTube.
I think we topped out at 18 on YouTube.
Okay.
I think we topped out at 18 on both the WebEx and on YouTube. So together, I'm calling it 36.
Thank you.
Did we record this presentation?
Yes, it is on our YouTube, and you'll be able to watch it as soon as it ends. So
that's good, because I missed some of it. Because of something else. Okay, thank you.
all righty. Well, thank you so much for the wonderful presentation, and I guess everyone can continue to socialize if you would like.
I'm afraid I have to head off now. But again, thank you so much for the invitation. I hope that you found this informative, and yeah, and continually keep looking out for news on exoplanets, because we're only really at the first stage in the discovery process at the moment. The second that we can look at terrestrial planets and we're just a few years away, everything will then start to change. And I'm sure there'll be some huge surprises that will come in the first few years after James Webb launches.
Awesome. Well, thanks again.
Thank you so much.
All righty, y'all. Well, I'm going to get back to my day job, which is increasingly becoming a night job. All right.
I feel bad for you, kid. I really do.
right, YouTube folks, good night. I'm ending the stream.
Good night, everyone.
Night.
Bye bye.
all.